also said that there are many kind of tools. So for example, lattice QCD and definition equations and the effective theory. Effective theory, I would say that I only mentioned several, but there are many others I didn't touch because I mean so many papers in this field. And I also introduced some efforts from bottom up, a holographic QCD model. And of course, this field is quite new, I would say, comparing with this field, because and of course it seems I think this started from 1960s or 1970s, and this is started from this just started from 2005, I would say. So. But still, we already, of course, there are also some NTU-CTP results for jet quenching and for transport coefficients, for example, eta over S, bulk of viscosity, and so on. And so basically, even though this field is quite new, but there are kind of many exciting results from this field. And I may try to give a kind of summary to compare different tools to handle this problem. So, for example, for light flavor hydrospectral, I think from effective models, for the ground state is quite easy, but for the excitation state it's quite hard. So basically, in order to get the excitation states, you have to put more and more and more and more terms there. So basically, your Lagrange is very long, right? So in principle, you can do, but you put more states and you put more parameters and so on. So basically, I think it's quite difficult to get such kind of rich behavior from such effective models. But for ground states, for example, sigma, pion, and so on, this is still okay. But for the full hydrospectral, light flavor hydrospectral, including SU3, I think this is still challenging. Well, not that challenging, but I mean, it works, but not very, I would say maybe not that good. I mean, for the whole spectrum, of course. But actually, for holographic QCD models, I think for both, I mean, for the light flavor system, for both ground, I mean, the ground states and the excitation states, this kind of quite easy. Well, of course, we also made a lot of efforts to get this correct. But in some sense, this comparing with this, this framework works much easier, I would say.
But they also include a barrier in your statement.
Yeah, we can have barriers. But
you can get a barrier excitation barrier.
Yeah. Well, I mean, actually, some people already got barriers. But yeah, but in principle, this is doable. Yeah, and also it seems even though it's very simple holographic QCD models, they can get barriers quite good in agreement with data. Yeah. So I think for this part, this is I mean, holographic QCD models and some advantages. But for me now, the problem is that I really have no idea how to introduce flavors. I mean, heavy flavors for the. So basically, I don't have any clue to get this heavy flavor hadron spectrum, and also and also very difficult to get this, to introduce U and S and, I mean, light and heavy, this kind of hadrons. I think this is also very challenging for us. I mean, in this framework. Yeah. But anyway, I think I mean, for hadron spectra, there are still many things to do. But considering this part, I think this is, I mean, this framework has some advantage than this. Okay, and then for the phase structure, I would say for the chiral restoration, for the chiral phase transition, I think the effective model, for example, this simple integer model or linear sequence model works well, because I cannot say works quite well because you never know, I mean, what's correct. Right? But anyway, it works. I mean, such kind of integer model or linear sequence model can grasp the main feature of chiral properties. I think for quark matter and for light quark matter, I would say for light flavor quark matter, I think integer model works quite good. And but the most challenging part for effective models is how to handle this deconfinement. Well, I mean, even for confinement, I mean, it seems from effective models, it seems quite, I would say, quite challenging, quite challenging for this part. But somehow, this holographic QCD model, this is very easy for deconfinement. So, I mean, so for gluon system, basically, it's so easy because even with Diniton gravity, you just need to introduce a Diniton, and this Diniton can give you can describe confinement and also deconfinement phase transition very well. So this part is quite easy. And this part, the chiral phase transition, actually, Dan is working on that, but and also we involved E with us. But this part, well, we're still working on that, but there are some problems here. But it is workable, but not that easy as this deconfined phase transition. And this is only but also another problem is okay. I think for phase transitions in such kind of holographic framework, so there is kind of some ambiguity with us because well, I mean, it seems, I mean, for us, I mean, from effective theory side, it seems, I mean, in this framework, there's something we feel a little bit uncomfortable because how to introduce this temperature and also this chemical potential. It's not very direct for us. Okay. And another important part is this actually I borrowed from Murray's slides, and so this is the hard QCD matter properties. I mean, of course from Rick physics people, they want to determine. So they want to have some equation of state. Of course, this part is, I would say, it's well done by Lattice people. And but for the transport, including this shear viscosity and also bulk viscosity, I think this is a little tough for Lattice people. And also, of course, recently there are two groups. They are trying to get this jet quenching parameter from Lattice QCD. And also some other conductors. I think for this kind of transport coefficients, I think it's still challenging for Lattice people. And of course, some screening is very easy for Lattice QCD. For the effective QCD model, I think this part is fine. I mean, of course, we missed something. I mean, for example, if we have a quark model, we will miss something some information from the gloom part, right? But I would say that this part is very challenging. If with productive QCD, I think it's calculable. But for strong coupling, I mean, when you go to no TC, no temperature, this is still very challenging. I think for effective QCD model. And of course, this is not that difficult. But still, I mean, we need a kind of effective model that we can, I mean, for moderate, I mean, close to DC, but not close, not asymptotically high temperature. So basically, I think for around TC, I think this is still very difficult. And for the holographic QCD, even though something we still we don't understand, at least for me, something still we don't understand too much. But it's quite easy, actually. I would say it's quite easy for. I mean, the framework is quite easy for all the calculations. But we need. I mean, the tools is very easy to handle such kind of things, right? But we need a kind of realistic holographic QCD model, which is really close to QCD. I think our model is one of the candidates. So we are going now. So we are trying to calculate the jet quenching at the moment, and also some other coefficients. And yeah, I think we have a lot of things to do, but also we need to understand this framework more or deeper because I mean, for me, it's really difficult to understand the physics from the geometry. You know, it's kind of what's there. Okay. So I think with this, I would stop here because I'm not good at the teaching because it's really okay. Thank you.
Any questions?
I want to ask a question about prediction power. Why it's interesting to find the gravitational theory? It gives you the correct mass spectrum. But once you got this spark theory, what kind of quantities can you use to can you predict?
You mean
with the potentials or geometry that you found?
Okay. So basically, I think we already have many prediction power because we have only 4 parameters, but we can produce the whole spectrum and also the Harvey couple potential and so on. So basically, if you read from the spectrum, you will see that with 4 parameters, if you can produce the whole spectrum, it's already some prediction power there already. Of course, I mean, but the important thing is that, as I said yesterday morning, that actually from the hadron spectrum we can read a lot of information.
I'm sorry, you say at the end you sort of can just use 4 parameters to predict some spectrum.
Yeah.
Could you summarize what spectrums that has been reproduced with these 4 parameters?
Yeah, this is a spectrum. So I think this is till now within this holographic QCD model. I think this is I would say this is the best one. I mean, in agreement with experimental data.
But I would say you can use the spectrum as your input to constrain your bulk geometry and potential.
So you mean from the spectrum you constrain the.
Right. But once you've done this.
Yeah, we of course, I mean, with the parameter, of course, are fixed by some, for example, pile mass and rho and yeah, and also.
I'm saying that
yeah.
You took the inputs from some other quantities, and this is all your prediction? Or I thought you take those as a prediction to fix your theory, no?
I mean, of course we fit several parameters. For example, M pi and rho meson, and I think another one might be chiral condensate. And all these are kind of our output, right? I mean, we took some several data from here, from the ground state, but all these are predictions. This is indeed very non-trivial because it's not that easy to get everything correct. And also we have this. This is, I mean, to get both this and this is the first time. And also to get this data, I mean, this spectrum so close to the data, this is also, I think, we did the best. I think I'm quite proud with Danny that.
Right, but I have the impression that everybody took those low 9 mass as inputs.
Yes.
But not everyone get the spectrum correct, right?
Yeah.
So in some sense, you sort of take the spectrum as your input, then you shoot for the correct parameters in order to reduce them. So in some sense, you have taken those.
But we took the same parameters. I mean, we have the same number of parameters as KKSS model. You know.
I see.
We don't have extra parameters.
I see. But by sort of optimize those parameters, the choice of of the parameters to get nice fit, right?
Yeah. So basically, yeah. So the only thing we did is that we solved this problem, this system completely. So we did the complete calculations and we get everything correct. So this means that the KKSS model is a good model because, but at that time they didn't solve it. They didn't fully solve this model because they took this ADS5 metric. Because with this they can get this linear ridge behavior for the rho method. Yeah, but of course this is the essential point for this ridge. So this model is, but now it's kind of okay. We just, so basically we did the work for them because, okay, we proved that, okay, your model is good. If you solve this fully.
Yeah, I have a comment about this mass spectrum because you just showed the main zone, right? So I asked about the burial, but I think the main zone also has that problem that I guess you fit them with the value with the PDG, right? Particle data group. And that's dangerous because when you go to the higher main zone, they have a very complicated decouple channel, and particularly in the burial. That become very serious, so sometimes it's not easy to really to know where is the mass because there are different schemes. Some even have used so-called usually the PDG group use this Bragg-Wigner formula to fit, but it's not a good fit. In particular, if there's a very complicated resonance overlap. So nowadays people are more keen to use so-called complex mass scheme. But the number actually shift a lot. So I doubt that if you fit this complex mass scheme, I don't know
we are not fitting this data. So these are our outputs. So we are using
I know. I mean, when I first time heard that, friend told me that KKS can do reasonably well. And then I asked what kind of mass you fit, let's say PGG, and I said, oh, no. Because when you really working on this resonance physics, you know, that kind of, the mass value is not as precise as your image.
Yeah, but the pion should be okay.
Pion, of course, but the pion is fixed by the chiral physics, right? As long as you put your quantum mass right, you make your condensation right, you always get the right value for the quantum mass, but the pion mass. But the non-trivial thing is excitation state.
Yeah.
That's highly non-trivial. So
exactly, this is what I want to say.
Yeah, so that's what the model guy have to be really careful to build out the correct Hamiltonian to give the right
You are right, absolutely right.
Yeah, but I have to say that to fit the PTG value is not as safe as you guys think.
Yeah.
Because I also have when you go to the higher resonance, you always will consider the decay and actually the mass actually shift a lot. Sometimes it's not that even easy to define where is this resonance mass at all.
Okay. But in any case, I think still this, for example, for this pion, it is really non-trivial because you see, so we can get this ground state correct and also this higher states, at least the tier here, this
so
is correct.
Do you show the tensor one and
Tensor is not here because we didn't know that before July that there's some problem for tensor.
But actual vector.
Yeah, actual vector is this one. So I think even for this is not that trivial.
Sure, it's not trivial, but
Yeah.
don't trust PDG value.
But then, if we don't believe PDG, then what should we believe?
Why should I come to people like us? I'm serious.
Presumably the error, the uncertainty you mentioned is in the error already.
But yeah, but sometimes actually you even have the difficulty to identify the resonance. Because some resonance is so wide. Right? So that's always so sometimes people even try to, so you have the 1 star, 2 star system, something like that, 1 star, 2 star, 4 star. So I always I'm sorry, but every time when I see this kind of fit, I always complain about it.
Yeah, okay, no problem. Yeah, I think actually within this framework, actually we cannot really get this situation.
Sure. I recognize that your result is a big improvement. But I just said
No. I mean,
if you make a too big claim, that you see this, you already catch the QCT very well. I still have some doubt about because of for example, can you make a prediction on the decay?
Yeah, this is what I want to say, that we at the moment we don't have such behaviors. Yeah, but we can do later.
Sure.
Yeah, but anyway, I think well, this is still very I would say even though this is non-trivial, but still a very small part of the whole framework because for example, you mentioned the barons and also heavy flavors and also the light heavy flavors. I think this is still challenging for us. But I don't know how far we can go. But well, I think this framework has some kind of advantage. But the thing is that still not a kind of first principle. It's a kind of okay, you can play with, but
it's more like a magic, right? Because here it's bottom up, so there's we don't really know that's how to start from the string side to come down.
Yeah, that part I will never touch because that part is kind of out of my ability because I think string people should work on that. But I like this picture very much. I mean this RG flow picture. But I mean eventually maybe we do not really need ADSFT. We only need this RG flow. If we can, but of course, maybe eventually the correct series that we have we have QCD at the UV region, and then we just do RG flow, and then we can get everything correct from. But this is what Yannis are doing. Yeah.
Yes. Any more other questions? If not, let's thank the speaker. Okay. This is the end of the summer school, but I also, on behalf of the organizer.